The next problem asks if your magnetic field is 0.005 Tesla times 2I plus 6J plus 8K, then how do the results of the preceding change? Okay, same situation but a different magnetic field. And this magnetic field is no longer perpendicular to your velocity vector. It's 2I. If your I is here, J, K, then you got 2 units in this direction, 6 in this one, and 8 in this one. So the direction is going to be kind of up like this. Okay, well, so again, the magnetic field is not going to be perpendicular to your plane or your velocity vector. Well, that doesn't change much, but of course there's some crucial changes. First place, the magnitude of this magnetic field vector is much greater than the magnitude of this magnetic field vector. Okay, it's at least 8 times as great in magnitude, and even more because of this, probably about 12 times as great, or 11. It's a whole lot bigger, but it's also, again, not perpendicular to the area region and not perpendicular to the velocity vector. So how do we deal with this? Well, it's fairly easy. The magnetic flux is just B dot the A vector. The area vector is just, again, area times the K vector. Of course, the area is changing with respect to T, and when we take the derivative, we'll take that into account, but we've seen how to deal with that here. Okay, so really all we have to do is take a dot product of B with the K vector and multiply that by the area. Okay, and B multiplied by the K vector, dot product of B with the K vector, the dot product with the K vector, the 2I is going to have dot product 0 with the K vector. The 6J will have dot product 0 with the K with respect to the K vector. And the 8K will have dot product just 8. So that out of this dot product of this vector with the K vector, we just get 8, which is then multiplied by the 0.005 Tesla of the magnetic field vector and the area A. So multiplying 8 by 0.005, we get 0.04 Tesla times the area. Now this is not a dot product, this is just a plain old multiplication. So that when we do the derivative of phi, the derivative of magnetic flux phi B with respect to T, well, the derivative of phi B with respect to T is still going to be the strength of the magnetic field multiplied by the area. This is constant. The area varies. How does the area vary? Well, the area varies such that its derivative is 0.6 meters times your 8 meters per second for the same reason it was before. And then when we multiply this 0.04 Tesla by the derivative of the area, we're going to get something very similar to this. We're going to have a 0.04 Tesla instead of the 0.005, but it's going to be multiplied by the 0.6 meter width multiplied by the 8 meter per second velocity. And we get then 0.192 volts. It's actually going to be negative 0.192 volts. You could say that the negative of your derivative phi with respect to T, which is going to be your EMF, going to be that. So that's going to be the EMF that you induce as a result of the changing area in the presence of a magnetic field. Now this generalizes. It's always the same. Phi B is B dot A, and if B is changing and or if A is changing, you still get an expression here. And if you have sufficient information, you're going to be able to take the derivative of that expression. The dot cross product, or dot product, might be a little more complicated. Maybe this vector isn't the simple K vector. Maybe it's got I, J, and K components, but it's still going to be easy to do the dot product. If the magnitude of the magnetic field is variable, then we would have a variable quantity here and a variable quantity here, and we'd have to use the product rule to find the derivative of the flux with respect to t. That wouldn't be a big problem if you just keep your wits about you and, of course, understand the calculus a little bit. It's not difficult to do.